Click the bell icon to get latest videos from Ekeeda.
Hello friends, today we will discuss about some extensions on the B plus tree index files. That is, we will talk about the file organization using the B plus tree index files. We will know how the index strings problem is being solved by the B plus tree index files, and also the B plus tree index files support the bulk loading. So we will discuss each of this case elaboratively. First, that the B plus tree can be here implemented in many of the portions on that DBMS. The first one is the file organization. As in the normal indexing file organization, the main problem is with the insertion and deletion of the index from that file. Now, when we have an indexed file organization based on a primary key index, not the B plus tree, so there can be a problem of that the indexing is based on the primary key and there is no tree hierarchical order maintained to it. Now, when we have such things, then we have the insertion and deletion become extremely problematic. Now, how it deals with? So, the first one is this index entries on this normal index tree on the indexed file organization that we have, that with the growth of that index, it actually grow out of order for that particular index. So now if there are n number of index to it, so it cannot just happen if there is belonging to n plus 1 number of index that is associated to it. Now in the deletion case also, if there is any index added to it, so we again need to check all the index and where to locate that index. Now we could have used the B plus tree file organization instead of the normal index file organization to remove these problems and have a better enhanced file organization on this basis. Now the B plus tree file organization supports that not only the nodes will store the pointer to the data, but also the last parent node, which is the parent of the leaf nodes, will point to not the pointer to the actual data, but the data combined with the search key with that index. That means the leaf node of a B plus tree file will have all the data that is associated with the search keys with that file, not the search keys pointing to the data. Now a level of indirection is here removed, which will remove the error for the index addition. So whenever there is an index addition, so it can go for like the leaf node and then finding the search key associated to it and then add the index to it. So the first one is, now the second one is the sorted key, that the key is sorted so that we can have all the keys put into the exact direction in which it can be put into the B plus tree file. Now let us see that how to use this file organization. Say suppose we have the range of this key. Now as we can see that I becomes the root node for our B plus tree. Now we have C, F and K and M as the immediate child of the I. Now for the C and F, we can accommodate all this A, B, C, D, E, because there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And already we will have 1, 2, 3, 4, 5, 6, 3 is 18 number of block pointers. So now we can accommodate all these 15 pointers in the leaf node. See here in the leaf node, not the pointers that the search keys we are containing, also the values that is matched with the search key, we had to insert it in the B plus tree file organization, so that there is no need to add one level of indirection pointer to the levels of the values. Now it has also got some problems with it because it will require that the number of attributes will be attached to this leaf nodes. So it will require a more space to this requirement of the leaf nodes. However, till the half of these leaf nodes are not full until and unless you have filled it with all the attributes. Now like this, the K, L and M also will have the values in it. Now the link nodes will be linked with each other through the values. So in this way we can have attached with all the values that is happening in this one. Now here we can see that there is no pointer in between this because these are the leaf nodes and they have all the values associated to it. So there is no need to add pointers to the leaf nodes. Now say suppose we are finding a search value v with an less than comparison to it. Now when we are finding with a less than comparison, we can start just from the right if it is a sorted one or a non-sorted one. So if we are finding from the last one, say for the f, so anything that is lesser than f, we can have this one as the leaf nodes are linked with each other. So we can find the a, b, c, d, e until f all the values if it is the sorted one, and also if it is the unsorted one, then also we can find the I on the j that is unmatched, or then a, or then e, then the match one with this less than v comparison. So in this way, B plus tree file organizations have become more popular and important to us while having all the trees on the leaf nodes and the values. Now what happens with the cost analysis with this B plus tree indexing? Now if there are n number of nodes on the leaf, then we can have, if there are 3 pointers, say one pointer, one is the search key, another is the value associated to it. So we can have at most 2n by 3 number of values that is associated to each of these leaf nodes. Now if their height of the tree is 3, then we can have 3 into 2n by 3 minus 1, that is still less than 2n. Now when this kind of situation arises, then we can say that we are having a B plus tree organization with double the benefits of the having leaf nodes, not only the associated values but also the search keys that is a pair with an associated value. So now what happens if this n increases to a large number? Say for example, there are 3n by 4 number of entries to a node of n with m minus 1 leaf nodes to it. So now it will have m minus 1 into m by m. What do you mean by m minus 1 into m? Because m minus 1 is the number of nodes with each n leaf node divided by m, that is the height of this tree. So in this way we can have the m minus 1 into n by m possibilities of generating the value paired with the search keys that we can have in the leaf node. So that will solve the problem of inserting the value into the B plus tree file or delete a value from the B plus tree file. Now we will show that how to insert the value into the B plus tree file. Now as in the normal of the insertion to the B plus tree file, we have that 3n by 4 number of entries if, then we can have the splitting up of node into 3n by 4 and 3n by 4 minus 1 number of entries, so that the splitted up nodes can have the entry or the accommodation for the associated values, that is 3n by 4 into n into m minus 1 by m, and both to this case. So now we can have at most number of leaf nodes that can accommodate a large number of entries that is indexed to it. So whenever an index is coming, we need to check the value for it and then place it either in the block of 3n by 4 or in the block of 3n by 4 minus 1, and then find the value that is associated with that index search key and then have the value located in this position. So in this way the insertion becomes extremely easy while having in the B plus tree file organization, where it was very difficult to put in the index file organization. Now let us talk about the deletion. Now the deletion is, we need to find the search key with the value v to it. Say suppose k is the search key with value v to it. So we need to find the position of v with the deletion, that is to find the node. If it is merging up the node with the previous one, that the node becomes the only one in that particular sibling. So if there are 2n by 3 position and 2n by 3 minus 1 position, finally 2n by 3 plus 1 position, then k is equal to v belongs to any of this. We need to find that one. If it is the minus 1, then we need to have it into the 2n plus 3. If it is the plus 1, then again we need to minus it to get the 2n plus 3. So now if it is the last value that is associated with the node, we need to delete the node for having deleted the value, and then again merging it down with this 2n by 3, making it the root node. Now if it is the leaf node containing with other associated values, then we can just simply delete the node. Now we will talk about the secondary indices in the B plus tree file index. Now when we are talking about in secondary index, that means already a primary index B plus tree is there. Now we are building a secondary index to it. Let us talk about the instructor relation. When we are talking about instructor, that can have ID as the primary index and say salary is the secondary index. So now when we have salary is the secondary index and primary is the ID. So we have all the values that is associated to ID here. Now when we have a secondary index and there is an insertion to the primary index ID, so what will happen to the secondary index? It will remain intact. So if there are 100 million entries into our relation, then we can have if 1 nanosecond for each of these million entries, so we will need 1 millisecond for each of the block and 100 millisecond for each of this entry to get inputted into our relation. But what happens if the is of the secondary index, if the insertion is made on the secondary index, now if the primary index also changes this value or updates, the secondary index remain intact. Say suppose the group of 51,000. So there can be a change in the ID value, so no need to update the salary until and unless the salary is being changed. So what is the advantage of having a secondary index that we can have in an B plus 3 index on the file organization? So if there is any change on the primary key, then we can have the insertion made on the secondary key so that we have a lesser number of insertion cost than the primary key indexing. Now when the relocation of the load on this requires that there is no need to put an extra one on the primary index. As in the B plus tree, we know that there is two possible insertion. One is the node that is attached with the values. That means there are already position for the value inside the node. We can just attach the value to the node. Another is the node is being filled up. Now we need to split up the nodes. Now if that is the case of the secondary index that is built on this primary index ABC, so we need to allocate the node on the ABC. We can allocate it along with the 51,000 that is based on this primary index. So that is the main idea of having the secondary indices. The next is the index strings. Now what happens with the index strings? Say suppose a string name with a variable length, the string name that goes along, a string name that is similar to many other strings on that field. Now each of these will happen to exact interaction with the relation that the string will context with the values, and the values can be larger to store in the leaf node. Now when the leaf node is storing such values, say silver scats. So when this type of storing on strings is needed, then there is no need to store all the long string. We can just store this particular 3 or 4 fields to it. Now if this strings that we can have this one silver and also, so now what will happen if we store the first 3 letters, then it will index with the same values. So it is of no use. Now we need to store the index strings as closest to as much variables or character in it so that it can support the distinct nature of each of the string. So now if we store 4 of the characters, then also it cannot store the uniqueness. So we need to store the 5 characters like SILBE, SILBI and SILVE. So now we can store the uniquely on the index on each of the strings. Now on the leaf nodes, we need to store only the index to the strings which will contain the values on a pointer to it. See, the pointer to the associated values and a pointer to an index string is entirely different. When we pointed to a pointer to an index value, that is an index string, that means it is referring to the value only. That means a value will already stored in it, and now we are storing only a part of the value to consume a lesser space. But when we have a pointer to the search key and the pair of the exact value, then we need to store all the values to it in accordation on the pointer removal to it. So that is the benefit of using an index strings in a particular B+tree file organization. The next one is bulk loading. What do you mean by bulk loading? Before that, we need to know if there are a larger number of entries in our relation, then to make an index on it, it will take a lot of time just for making the index. Say for an example, we have 100 million entries in our relation, and each of these entries will take 10 microseconds to actually have their entries indexing. Now all the indexing will only need, that is 100 millisecond to create just the index. Now this is a large time if compared to building the database. That 10 millisecond or 100 millisecond is needed only to build the index, not the entries in the database. Now if we just change it to the bulk loading, what happens in the bulk loading? We first sort the data, that is the index on that particular file. So we create a temporary file ti and then make the indexing to it. So not the database we are storing, we are actually storing the indexing to a temporary file ti and then create the sorting on that ti. After the sort ti is being called, then the temporary file is being sorted. Now we can put this sorted ti as our index to the database. Now the sort ti has been made the index, so that the index can now could be the blocks, and then finally the blocks can be put to the relation. So here the filled entries are be considered to be as the blocks which is being indexed by the index values, that is sorted out. Now what is the benefit of sorting it out? After that we are having the sorted result on the index. We can create the blocks with a relation that is lesser than or greater than to it. So whenever, say suppose I want to create an index on salary 50,000, so any salary that is greater than 50,000, we have to look only the greater than blocks to it, not the lesser than. So in this way it will just reduce the 100 millisecond to only 10 millisecond creating the index, because it is being sorted out and we are just storing the blocks to the relation, not the actual entries to the relation. So here the secondary index is being the index field, blocks is the primary index to point to the records on that field. So in this way bulk loading improves the relational expression of an B+tree file organization with the help of the features of an B+tree, just like the pointers or the node accommodation of a parent node that can help with the entries indexed to the leaf node. So now all the record that we have put in the blocks and then make it into the index to it, so the parent node can find and index to the leaf nodes that has the values to it. Now as if we have all the leaf nodes with the values of the entries and the parent node to it as the pointers or the index, then we can say that we are following a bottom-up approach on the B+tree construction. Now what happens with an B+tree bottom-up constructions? It will first store all the values in the leaf nodes and then create the index based on it. So it will take a large lesser number of indexing time rather than having the disk access time. So also the disk seek time will be lesser than the other comparison index trees that were built in this hashing. So now we can have the B+tree index file ready for the sorting, for the bulk loading, for the index strings, as well for the organization of a large data relation. So thank you for watching this video. Stay tuned with Ekeeda and subscribe to Ekeeda.